Now let's talk about the important factor for computing Phong. I'm going to actually refer to the Phong illumination model here on Wikipedia. Yeah, this one. Let me clear those like annotations. I'm bothering. So here is the kind of the article about Phong. Phong has three. Phong is a model of light that actually divides the light into three main components. One called ambient, one called diffuse, one called specular, and then when you combine the three, you get the Phong illumination model that looks like this. I don't have time to kind of go over and like describe this in detail, but to compute these three components, we're going to need some vectors, and these vectors are kind of illustrated here. Okay. For the ambient, you don't need any vectors. For the diffuse part, and here actually, this is the formula that combines these three components. So this plus sign here, this is the ambient component, this is the diffuse component, and this is the specular component. Okay. So for the ambient component, you don't need any of these vectors. For the ambient, you need the Ka, which is the reflection constant, or it's a ambient reflection constant. So you can think of this as a kind of a RGB value. And also this is another RGB value, which is the intensity. The I is the intensity of the ambient light, and the Ka is the reflection coefficient of the material. So this is actually four variables here. You can think of these four variables, Ks, Kd, Ka, and alpha, as kind of the material. This is the material of the object. So those are properties of the object that it can change. So for example, if you want to change how much a certain object reflects to specular, you're going to change the Ks. And you can, for diffuse, you're going to change the Kd. So every object has a different set of these variables. These are vectors that are highlighted, that are illustrated here. And these vectors are going to be computed in the shader, because you're going to need them specifically for the specular, for the diffuse and the specular. So for the diffuse, we need the normal and the Lm. The Lm is this, the L is this vector here pointing from the vertex towards the light. So you're going to compute the dot product between the normal and the light direction. So if you note the assignment, you're gonna pass a point to the shader, and then in the shader you have to compute the vector from the point minus the vertex. Okay. So we're gonna have to pass a lot of information to the shader to get these vectors going, to get them here. So let's first talk about the light, and then the view. So this V here is another important vector, which is the vector from the vertex to the camera. Okay, so you're gonna have to compute this as well. Okay. So let's create a uniform here in the fragment shader. Remember, all our color computation is going to happen here in the fragment shader. So I'm going to make a new uniform for the light position. I'm going to call this U light pos. Sorry. Okay. So again, we're going to have to make a variable in the JavaScript here. Call it U. I'm going to grab from there. U. What is the name? U light position. I'm sorry, and this is a vector 3 as well. It's a position in the world. So I'm gonna define this here. Oh, that's weird. Why is it like oh, it's a capital thing. Okay, and maybe this, let me remove that capital from there. Okay. So again, we're gonna read this guy. Retrieve uniform. And we have to pass the light position. Okay. So light position is a vector 3. I'm gonna update here, update the light position in the shader. This also should be in the shader. You can do this with GL uniform 3F light position, and then we have, we can do 3FV. We're gonna have to create a light position, okay? And actually, let me make this after everything. I'm gonna make a vector here. Pause. New vector 3. Let's put it up. Let's say. So this is straight up from the origin up. I'm picking like a light position, just an arbitrary position. And here you can pass light pause dot elements. Actually, just making sure this is a new float32 array as well. No, I think this is fine. This is already, it's already float32 array. Specify a light position. Again, this is a position. Even though I'm representing as a vector, it's actually a position. Okay. So, okay, that's it, I think. Let me just, and here, we're gonna use it to compute the vector L. So the vector L is what? Is this, which is the light pulse, minus this. What is this? This is the position, right? This is the vertex. So this is the A position. And this is weird because we only have A position here, right? So I think we're gonna have to pass a variant. I think you're gonna have to do actually a variant here. A vector 3 V position and pass the V position to the fragment shader. And then here we can do this. And this is our L. Okay. And let's normalize this as well. We're gonna, if you look at this formula, you see the kind of hat on top. This means that this vector is normalized. So let's normalize it here as well. So all these actually vectors are normalized, okay? So light position. So we have L. Let's see if this is working. Let's see if it's kind of running or something. Maybe like bugs. Oh, That's cool. Let me use this vector L here. Let's see what happens. Nice. So what's going on? L is the light position minus the position of the vertex. So light is kind of straight up. Actually, oh, it depends. Actually, where is the object? The object is actually centered. I am the camera is at -10 on the Z. So yeah, the object is actually at the center. So the light is kind of up here. Oh, where's my shader? The light is up here. So let's see what's going on. This is green. This is, and this is like 0, 10, 0 minus 0 minus 1, 0, normalized. Does it make sense? Like 10 minus, let's say 10 minus minus 1, it's 11. Normalize is equals to 0, 1, 0, which is green. Okay, I agree with this. Do you agree? All right, this makes sense, right? Yeah, and then, yeah, this is red-ish. So let me see, where's the red part? Yeah, the red is on the, yeah, it's kind of tricky actually, but I'm satisfied with the green. Green is easier to debug. The blue is in front of me, and this is probably like the brightest blue. This is 0, 10, 0 minus 0, 0, 1. So this is 0, 10. This is 0, 10, 1. No, 0, 10 minus 1. No, my bad. 0, 10 minus 0, 0, 1. 0, 10 minus 1, which is clamped to 0, 1, 0. Wait. I think 0, 10. Wait, 0, 10 minus. Oh, this is positive. So 0, 10, 0. This is negative, sorry. 0, 10, 0 minus 0, 0 minus 1. So the result is 0, 10, 1, which then gives us 0, 1, 1, which is cyan. Yeah, I think this is, yeah, this makes sense. Okay, I think this is correct. Yeah, and then yeah, I think this is correct. It's hard, but I think this is correct. Yeah. What? Okay, but this is our L. We have like 12 minutes to finish. This is our L. First, we now need this V. Actually, let's compute the R. The R is straightforward because it's the reflection of the light with respect to the normal. So vector 3R, we have a reflect version of a function here. That's why it's straightforward. We can do reflect L. With respect to normal. And then again, this is normalized, so let's make sure to normalize this too. It doesn't hurt. I don't know if it guaranteed. If you rotate a unit vector, yeah, actually if you rotate a unit vector, you for sure get a unit vector as well. I mean, you're not changing the scale. You're not changing you only change the direction of the vector. You don't need to normalize it. It's up to you, but you don't need to. So this is R. Let's try R here. Okay, we got something. It's funny, we probably got something like make kind of the opposite of the L. Not opposite, but the kind of the reflected version. No. Not the L, the N. Let's look at the N. Yeah, this is N, and this is R. Huh. Yeah, now it's hard. Now it's hard to see what's going on. But I'm sure that the R has some values. I recommend you trying to make sense of all these numbers before moving forward. You can look at the colors and see if the colors make sense. We don't have much time here now, but I think this is correct. Also, because this is correct, this has to be correct. So next step is the V vector. And perhaps, I think this is the last one. The edge here we actually won't need. This is the outcome of the computation here. But the last one is the V. So V requires the position of the camera. So here we're going to actually have to give the camera position as well. Another uniform, okay? So, okay, another uniform. We have to go down there, click another uniform for camera position. And then retrieve the uniform. Okay. And then set. But now it's tricky, right? Because now the camera is moving. So we have to do this in the loop. We have to update in the loop here. After updating the view matrix, let's do it. Let's update camera position in the shader. And this is u underscore camera position. And we need to pass the camera location, which is camera.I elements. Okay. I just realized something. Let me see. No, this is correct. And that's it. That's it. No, nothing. Yeah, I think this is fine. Yeah, we send the camera position before drawing. And that's fine. And now you update, and this is the right. And this is this guy. And then here, now we can compute vector 3, our V, which is similar to the light position, but it's u underscore camera position minus V position. All this normalized. You see, this is the vector V from the fragment to the eye. Okay, now let's see what happens here. Let's see this V. Wait, there is some problem here, right? Invalid value, uniform, invalid size. Where is this? 106. Oh, this is not a matrix. This is uniform 3FV. Yeah, sorry. I was trying to copy. This is a vector. This is a position. This is a vector 3. So we have to set it like this. And camera position. Oh, cool. So it's all dark, but as I move the camera, I can see that it's changing. And this is expected because the difference, the L changes as I, oh, that's cool. So now L is equals to 1, V is 100. That's why this is all red, right? And this is 100 because I am at, yeah, probably like it can happen in different scenarios, but yeah, that's cool actually. Like if you move the camera, you see the color changing, because, and this is expected. So yeah, so this looks right. This looks right as well. At least this behavior is expected. At some point it's all dark because this is all negative values. This is all the negative values of the vector V. And then as I start going around, then it starts to get positive at some point. Wait, what? No, that's weird. Wait, let's see. Oh, maybe, I think maybe I have to go for. That's funny. How did I? Huh. Try to. Yeah, I have to go. Actually, I have to go to the other side. Oh, now I'm gonna lose it now because I don't know where I am. Yeah, it was there. Yeah, I think this makes sense. I have to kind of debug. It's very important when you're dealing with lights, debug all these values, but this looks correct. I've seen this before. I just wanted to actually think about this. And whenever you are implementing these steps, always debug your vectors. This is very important. It's key for getting this right. Otherwise, if you try to do it all at once, really don't avoid this as much as possible. If you try to just, for example, copy the code from somewhere and then paste everything in and then debug, it's going to be a mess. It's going to be almost impossible to get this right. I highly recommend you going step by step like I did here. Now, once you get all these vectors right, then computing the whole formula here is very straightforward. Okay? For instance, I can do this part here with you right now, just to finish this lab. We can actually compute the diffuse light or diffuse component here, and you can say diffuse equals 2. So diffuse is this part here. And I'm going to assume KD is vector 3. I'm going to say it's 0.500. So it's kind of like a low red color for that light. So that light is yeah, if it's only once is a bright white color, I'm actually making a red color, a red light. So this is our key. Okay, I can actually do this here. Vector 3. I'm gonna call this KD. You're gonna have to pass the KD and the KD and KS. You're gonna pass as a uniform as well. but I'm actually defining here a hard-coded just for this assignment, just for this example. But this is going to be KD times L. There's a function dot L with N. Right, I'm doing this part here. Times KD. I'm going to disregard the intensity of the light, this IM component for now. This is the intensity. This is the light color. And this KD is the material, the reflection, the diffuse reflection from the material. I'm going to assume this is 1. This is 1, 1, 1. Later, you can actually, you can pass this as a uniform as well. And this is actually 0.500. So because the dot product can be negative, I'm going to do this max with 0. I don't want my diffuse light to be negative, because like negative colors don't make any sense, and I want this to be, and then whenever you see like whenever this number is negative, it means exactly. So I want to think about it, but if the light is in front of the surface, this dot product is going to be positive. In other words, if the N and the L have an angle that is less than 90 degrees. So if this angle here, N and L, if it's less than 90 degrees, it means that both of these vectors are pointing kind of towards similar directions. So they're not opposite to each other. But if L starts going down here, at some point, there's going to be an angle that is bigger than 90, and then the dot product starts to become negative, which means that the light is, imagine like the light going around the Earth. At some point, the light is going to be, let's say, here. If this is the US, right? You're going to be here, maybe like in Australia or something, and then it's day in Australia, and it's a kind of night for us in the US. Okay, so in this case is like the light. It's the angle between the light and the normal is more than 90 degrees. So this is when, if the angle is bigger, is greater than 90, this dot product is going to be negative. So I want to make it 0, which is black. Like whenever it starts going to the side, I want this to be dark. I don't want this to be any light in here. That's what I'm saying with this max. And then I multiply by the reflection coefficient from the material. And this is my diffuse. This is my diffuse component. Let's see. What did I do? KD times max. Oh, vector 3. This is a vector 3. It's a color. So this is a color. This is a diffuse light, but also this is an RGB. This is a light color for the diffuse component. So we're going to get something similar to this here. So this. So the light is on top. Let's move the light. Light is actually on top. You're seeing all dark. Let's move the light a little bit. Let's put maybe 10, 10. Also, let me make sure. This is, let's see, 0.5. 0.5. Oh, what is I think this is always giving me 0. Because the light, yeah, I have to figure out where to place this light. Try something -10. Maybe like 5, 5, 1, 2. Huh. It's funny. Diffuse KD. L. Light direction and the normal dot product. And the only explanation is that this is getting me 0 all the time because of this L. Let me just try something here. Let me just, yeah, just for debugging. Huh. I see. Yeah, now it's correct. It's gonna be like a little bit bright red now. Where is the, but we should see some, where the light is, we should see some, maybe it's too like, let me see if I put this, let me start this at 0. And this is 0, 0, 1. No. Huh. Yeah, this is a small bug. Yeah, this is a bug I have to figure out. This is, no, this should be like before. This should be like this. Yeah. Unless I'm doing something wrong here, via position. Yeah, this. Oh, I see. I see, and actually, it's good that we saw this problem, and I forgot. I know it's kind of a little bit over time, but I wanna finalize with this, which is an important idea, which is our position, A position, is, note that our A position is our vector vertex values. And our vertex values are always defined in the object coordinate space. This means that these numbers are relative to the center of the cube, for example. So are the sphere ones. So for the spheres, where's the spheres? Yeah, this is a very important actually concept, idea, or detail that you have to do. I almost forgot. These points are all defined relative to the center of the sphere, not to the center of the world. We use in the shader, and pay attention to this, we use in the shader, when we do this multiplication, where we are essentially transforming the vertex from the object coordinate space to the world coordinate space. But here we are passing the object, the V position, and this is the object coordinate space. So we need here to multiply the A position you have to do this here. And what's the best way of doing this? Actually, okay, I'm gonna, for now, just cast it again back. We have to multiply past the V position in in the world coordinate space. Before, so see that we don't want the view and the projection. We don't want to consider, because this is mapping to the camera coordinate space, and we don't want that. We want everything to be in the world coordinate space. Why? Because the light is defining the world coordinate space, right? The light position, the light position, where is the light position? This is relative to the world. So for example, this can be 10, whatever. So this is relative to the center of the world. We have to also give that position to be relative to the center of the world. That's why we were seeing something weird. So now let's put the light back on top. Like this is now 0 straight up, 0, 10, 0. Okay. Yeah, thankfully we saw this bug actually, because I was almost forgetting this. Okay, so now I think this calculation makes sense. These both calculations make sense because they are all happening. And so the camera also, like the camera position, or in other words, the eye position is always defined in the world coordinate space. So now all these numbers are in the same coordinate space because we now did this multiplication here. Let's see. Oh. A V position. I hope I didn't. Oh, this makes sense. And now let's see something here. If you put, this didn't fix it. But that's for sure something that we were missing anyway. Yeah, I don't know why is this light, because the specular only needs the light and the normal. The normal should be fine. Again, let me just change the order here, the direction of the vector. Same result. Anyway, I think we are getting a little bit over, we're already like 15 minutes over time. I'm gonna fix this and submit this code. Yeah, now we should see kind of like we should see a brighter spot here and like this part all dark. So this is not right. Yeah, this is not right. And because also this shouldn't be like this. I have to figure out why this is happening, but this is for sure correct. Unless this model matrix is wrong or something. But the normal, or maybe the normal, we saw the normal and it was fine. Anyways, I don't want to take too much of your time. I'll let you like ask you any final questions if you have. Otherwise, I'll fix this and like post to Canvas. Okay, yeah, cool. Be careful when you are implementing this. As you saw, like it's a lot of uniforms, a lot of variables. Like the shader is now getting a little bit complicated, and it's very easy to mess up. So go like step by step. Yeah, go step by step. Like get the diffuse right. Make sure the diffuse is looking good. And you can use these guys as references. Right? For example, the diffuse, we see that we get, so in this image, the light is probably to the right here. So on this like the back of this object, you don't see a lot of light. You should get like an effect similar to this, right? And the specular, for example, specular depends on the camera position, right? The specular changes if you move the camera. So this is something that you should see as well. The ambient is the most straightforward. The ambient actually is what we saw before. But yeah, it's unfortunate that we didn't get this to work. I'm gonna debug this and see. But yeah, be careful and good luck with that. And let me know if you have any questions by email or on Piazza, okay? I'll see you next time.